this continues chapter 5, now talking about the work-kinetic energy theorem, which will deal with practice C problems. First thing we have is our definition to the work-kinetic energy theorem, which is quite lengthy, but I think it'll help you understand the necessary, or why it's necessary to talk about work and kinetic energy together. So please jot down the net work done by all forces acting on an object equals the change in the object's kinetic energy. So continuing with that, or one more time just to recap that, the net work done by all forces acting on an object equals the change in the object's kinetic energy. So with that in mind, we have mechanical energy that we need to discuss first. And this is the energy required by the objects upon which work is done. So work is going to come from mechanical energy. Okay, so kind of think about that. Energy which possesses, or is possessed, by all objects due to its position or motion. So this is really the key concept I want you guys to get from this slide. So highlight it, star it, circle it, whatever. Mechanical energy is the ability to do work. So if you're talking about being able to do work, you have to have energy. Well, if you think about work, work is looking at your net force times your distance moved, cosine theta. So if you have a force and a distance moved that is not equal to 0, what type of energy must you be working with? You must be working with kinetic energy, right? Because kinetic energy is talking about energy of motion. So therefore, to put it all together, the work-kinetic energy theorem should make perfect sense. In order to say that there was energy in the system, it is the ability to do work. That's exactly what this statement is trying to tell you. That mechanical energy is the ability to do work because you moved some distance based on a force applied to it, parallel. Therefore, the object moved, kinetic energy, velocity. Remember, your KE is 1/2 mv squared, whereas velocity is the variable that will tell you what type of kinetic energy you're dealing with. A little bit more specific here, there are two forms of mechanical energy that you need to be aware of. Obviously, we just discussed kinetic, so what's the opposite of kinetic? The opposite of kinetic would be potential energy, whereas kinetic energy is energy in motion, and potential energy is stored energy in the system. A wrecking ball is a good example. Technically, this is actually a really good example of the work-kinetic energy theorem. From that, it says the massive ball of a demolition machine possesses mechanical energy, the ability to do work. When held at a height, it possesses mechanical energy in the form of potential energy. As it falls, it exhibits mechanical energy in the form of kinetic energy. Makes sense because it's moving. As it strikes the structure to be demolished, it applies a force to displace that structure. In other words, it does work upon the structure. So based on the kinetic energy, work was achieved. Another example is with bowling ball and striking the bowling pins. So as the bowling ball is moving, it has a ton of kinetic energy, and it pushes that kinetic energy onto the bowling pins who are now colliding. This should also make sense on how work, energy, and collisions all come into play. So also with momentum of the objects. Okay, so an equation here. Think back to what the change in means. If you talk about the change in something, then you're taking final minus initial. But I want you guys to really be specific. Once again, it's the velocity that the kinetic energy is going to depend upon. So your mass really isn't changing, right? Like maybe you're running around, you're sweating, you're losing some quote-unquote weight, but your mass is going to be equivalent. So it would be VI squared, whereas KEF would be 1/2 mVF squared. So looking at the work-kinetic energy theorem, the equation then becomes, this is the equation I want you to become comfortable with, W net equals delta KE. I'm going to go on a side tangent here for a second. So that means if W net equals delta KE, that F net times D times cosine theta equals KEF minus KEI. And then you would be able to break the problem down from there. So on this, you're probably going to have to draw a free body diagram to figure out what the forces are that are working on the system. Also, make sure that you look at what are my velocity values when you started the problem off. Because maybe it said started from rest. If it says started from rest, then your KEI is going to be equal to 0. If it says came to rest, then your KEF, because VF would be 0, is going to be equal to 0. This right here, excuse me, this slide right here is more so just looking at your mechanical energy and how your KE is all being converted to PE and PE being converted to KE. And this is with just mechanical energy. Because if you stop and think about it, this isn't a true scenario. This person is like skiing or snowboarding or whatever down this hill. And when we do that in real life, there's some sound that is dissipated, right? There's some heat that is created. So some of that mechanical energy, PE to KE, is actually converted into non-mechanical friction energy. And that those forms would be heat, light, and sound. So although this is a really good example, please make sure that you do understand that in real scenarios, not ideal scenarios, that friction is present and that not all mechanical energy is conserved. Some of it has been transformed or dissipated is a better word into non-mechanical energy in the forms of heat, light, and sound. Okay, so some examples here. Please make sure that you do, just for time's sake, I'm only going to do one of them with you. Do go to this slide here and you look at physicsclassroom.com. Please look at that before you do any assessments with us in this chapter. We do a lot with the work, energy, and power. So over there on the left-hand side, I can't really touch it because it'll take forever to get back. But on the left-hand side where it says physics tutorial, read down to where it says work, energy, and power. That's where I am. Please make sure that you read through this stuff. From that, then, you will be able to do these examples right here. So the first description says, a ball falls from a height of 2 meters in the absence of air resistance. Well, what's the ball doing, guys? The ball is speeding up, okay? It's speeding up and it's losing height. Well, if it's speeding up, it's gaining kinetic energy. So this example should be PE to KE. Click on C answer, and it is PE to KE. The ball is losing height because it's falling, thus gaining speed. Thus, the internal or conservative force, which is gravity, transforms the energy from a height to a speed. In other words, from a PE to a KE. So you try some more of these examples on your own and then see what you still need help with, what doesn't make sense, and then hopefully what does make sense. This brings us to our sample problem. So our sample problem says, on a frozen pond, a person kicks a 10.0 kilogram sled. Get your calculators out, please, okay? Don't just copy this down. Get your calculators out, please. Giving it an initial speed of 2.2 meters per second. How far does the sled move if the coefficient of kinetic friction between the sled and the ice is 0.10? Okay, so you kick this thing, it goes opposite direction of, it goes in a motion, but the force is what you're trying to compare it to. So since you are comparing it to the direction that the object's moving and force is working opposite that direction of motion, the theta that we are dealing with in this system is 180 degrees. And then you are trying to solve for distance in meters. So your original equation is W net equals delta KE. And I'm going to break this down just one side at a time. So your W net is going to break down into F net times D times cosine theta. Delta KE is simply KEF minus KEI. Okay, so now I'm just going to concentrate on the blue side. Looking at your free body diagram, the object is moving this way, okay? The object's moving this way. You don't have an applied force here, right? It was there, but it's not still on there. So it's just the F of K that it is versing. So your F net, more specifically in the x direction, is just simply F of K times D times cosine theta. Well, f of k is really mu k f of n times d times cosine theta. F of n is really f of g, which is mg times d times cosine theta. Okay, so now KEF. KEF is simply going to be, oh yeah, we need another given over here. It comes to rest eventually. Yeah, it doesn't say that specifically in the problem, but guys, come on, there's friction in this system, and you just shoved it, right? You aren't continuously applying that force. So since you were not continuously applying the force, eventually it's going to come to rest. So VF equals 0 meters per second, which means KEF equals 0 meters per second. So negative 1/2 m VI squared is on this side of the equation. So now what we want to do is put it all together and rearrange for d, because d is what we're trying to solve for. So that would be negative 1/2 m VI squared all over mu k mg times cosine theta. That would give us negative 1/2 10.0 times 9.81, which I apologize, I forgot to write it as a given. Please make sure you write it as a given. Times cosine, ooh, sorry. Going into the denominator there. 1/2 10.0 times 2.2 squared. All of that divided by 0.10 times 10.0 times 9.81 times the cosine of 180. Okay, so put that into your calculators, please. Get a numerator answer, get a denominator answer. Please try this out. Please don't just sit here and let someone else finish it for you. While you guys are solving this out, those of you that are good at math should have been able to see that your masses could simply be canceled out and you just had 1/2 VI squared over mu kg cosine theta. That's totally legitimate to do as well, guys. That would have given you the same answer. So looking at your calculators should have said 2.46 blah 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 blah. But if you look at your givens, you only want 2 sig figs, so 2.46 is okay to jot down. I'm just going to simply put the final answer right here. So your d equals 2.5 meters. More specifically, 2.5 times 10 to the 0th meters. Okay, quick question. Those of you that did not put this in your calculator are asking right now, why is there a negative there? Why didn't the negative carry through? Negative didn't carry through because the cosine of 180, make sure you're in degrees and not radians. The cosine of 180 is negative 1. So negative blah, blah, blah divided by negative 1 is going to give you a positive answer. So therefore, your final answer should be a positive value when it is all said and done. Okay. Wow, that D just does not want to work. Okay, so now go ahead and try your practice C problems in which the correct answers are on my teacher page.